Okay, next up is current. So, as I mentioned in the first video, current simply means the movement of charge, the generation of electricity by the movement of charge. Officially, current is equal to the amount of charge passing by a point in a certain amount of time. So the amount of charge passing by a point in a certain amount of time. If we measure, 1 million electrons going past a point per second, then that will correspond to our current. So it tells us how fast the electrons are moving, where they're going, and what they're doing. So if I have a very basic circuit, just my favorite, just with a lamp, and I want to measure at this point here how much charge is passing me every single second. Well, in order to do that, I would measure the current and I would pop in an ammeter in a circle. It's a circle. I pop in an ammeter. And if you're already familiar with ammeters and voltmeters, you may know that ammeters sit in series like this. They go inside the wiring, whereas voltmeters sit on the outside. Now, I'm not going to talk about voltmeters here, but the reason that the ammeter sits on the inside of the wire is because when my electrons flow this way, not conventional, but this is the way that they really flow, and they enter my ammeter, I can count kind of how many of them are passing me every second. And that is quite simply the definition of current, the amount of charge passing by me in a certain amount of time. So the higher the current is, the more charge is flowing, the more electricity is generated. So current is a very, very good basic unit for understanding the amount of electricity in a system. It is measured in amperes, which are a base unit. Amperes are one of the 7 base units. I did do a whole video on base units as well, meaning that they are a unit that we use fundamentally. We don't break it up into anything else. So all other units we use in electricity are made up of combinations of things like amperes and seconds and meters and maybe kilograms, but probably not, etc., etc. So we measure it in amperes, which of course is with the letter A. Last bit of notation, current, maybe quite confusingly, is represented using the letter capital I. Unfortunately, C was taken. Little c is a speed of light, big C is coulombs. We had to use a different letter. We chose I. Don't know why I'm saying we, like I had an involvement in that, but it was chosen that that would be I. So that's your bare basic look at what current is. But let's have a look at 2 more kind of details about it that are very, very important to know. The first one is known as, why am I doing lowercase? I don't know. Kirchhoff's first law. That's annoyed me now. Capital K, Kirchhoff's first law. And Kirchhoff's first law talks about, didn't see anything. Kirchhoff's first law talks about this idea of conservation of current. So in the same way, when we have energy in a system, we can neither create it nor destroy it. We have a similar idea with current. Now, it's not exactly the same, but we use it to apply at what we call a junction. So imagine I have a wire traveling along, and in that wire I have 10 amps of current. At a certain point, this wire may split. And it may split, like that. The whole idea of Kirchhoff's first law is saying that at this junction, no current can be created or destroyed. So it's not as general a rule as energy. With energy, current can never be created and never be destroyed. But with Kirchhoff's first law, we're just talking about at a junction. So the point at which a wire splits or a wire forms, into one. So before and after this wire, we should have 10 amps. Now, Kirchhoff's first law doesn't necessarily tell us it will be the same. It doesn't tell us that that has to be 5 and that has to be 5. That could be 9.8 and that could be 0.2. It really depends what is going on the wire. If there's a wire with a lot more stuff happening, a lot more lamps and resistors and things like that, it's probably going to take a bit more of the current. So we don't really know the exact makeup, but what we do know is that it will always add to 10. So 7 plus 3 will add up to 10. And this applies no matter how complicated the junction looks. So a junction also exists if I have, I'm going to go really crazy, 3 wires coming in, let's say 5 amps, 6 amps, 7 amps, and then 2 wires coming out. The current in these 2 wires will always add up to these 3. So what's that? 12, 18. So these 2 will add up to 18. Again, not necessarily 9 and 9. Could be 17 and 1. I'll put it as 10 and 8, just because I don't want us coming away from this thinking that it has to be equal, that has to be 9, that has to be 9. So I'll offset it a little bit to get that point across. So a couple of things. How do we know where the junction is, what direction it is? So for example, how do I know that it isn't 6 plus 5 plus 10 is equaling 7 plus 8? Because quite often, especially in exam questions and real life circuitry, you'll have many wires coming into a junction and you've got to work out which is which. Well, the answer is you use the arrows, okay? These arrows tell us where the junction is. So these arrows tell me I've got 3 coming in from the left and going right, meeting at a point, and then I've got 2 coming away from that point. So I can actually change these arrows and these numbers to make this no longer true. So I may actually have something coming in this way, something coming down here, something coming down here, and then something going that way and something going that way. Now, these arrows are completely different. Now, I need to focus on what have I actually got coming into the junction? Well, I've got 1, 2, 3 coming into the junction and 1, 2 coming out of the junction. Just look at the direction of the arrows. What I've done is I flipped it. This one used to be going this way. This used to be going into the junction, but it no longer is. It's now going out. Same with this one. This used to be going out, now it's coming in. So this completely changes the dynamic of the junction. So let's give some numbers. Let's say that's 6, that's 5, and that's 4. That's coming into the junction. So I've got 15 coming into the junction. So coming out, I also need 15. So let's say that could be 10 and that could be 5. So the official way of writing Kirchhoff's first law is it is the sum of, this symbol means sum of if you haven't seen it before. So adding up all of the currents that are coming in, and that equals all of the currents that are coming out. So currents in equals currents out, and it's always important to add them up. So always look at the arrows and ask yourselves which is coming in and which is going out. Okay, quite exciting. I might do this video in one take. That never happens. I always mess something up. Shouldn't have said that. Why do I say things? Yeah, not only did I not do that in one take, but this part's taken me so long to record, I've literally moved. So excellent stuff. Hopefully the lighting's okay in the second half. But now we've had a look at Kirchhoff's first law, I just want to have a look at the last little bit to do with current, and specifically one last equation that we can use. So instead of just stating the equation, what I would like to do is I would like to almost derive it, so show you where it's coming from. So I'd like you to consider a wire, okay, with a certain width to it and a certain number of charge carriers, but for now we will just call those electrons flowing through it. Now, there's a couple of things about this wire that I want us to take into account. The first one, and I will switch colours, is the volume of this wire, okay? V. The volume of the wire, and that's going to become important in a second when we talk about something called number density. Now, the number density, this is a term used all across science, not just with current, means the number of something, in this case the number of charge carriers or the number of electrons in a certain volume. So number of electrons in a certain volume V. So in this case, in this volume here that I've drawn, there are 6, but let's not get too into the numbers. There'd definitely be more than 6 if this is a real wire. Okay, so I'm going to use these 2 pieces of information here to construct something that will tell me the total amount of charge passing through this certain volume. So the number density, which is little n, that is a number density. If I were to multiply the number density by the volume, then I will end up with the total number of charge carriers within this volume. Yeah, because number density is a number of charge carriers per volume. So if I times it by volume, I just get the number of charge carriers. So if I then times that by the charge on each one, and I will keep that as Q, but if these were all electrons, it would be just multiplying by E. But I'll keep it general as the charge on each particle. Then I get the number density times by the volume times by the charge on each particle will give me the total charge within this volume. So now I want to draw our attention back to current, and remembering that my main definition of current is that it is delta Q over delta T, the change in charge over the change in time, the amount of charge passing by a certain point in a specific unit time. And what I'm going to do is say that, well, I've just worked out that that's my total charge, so I can actually replace my Q up here with this little expression here. So I get NVQ over delta T. And I get that my current is equal to the number density times by the volume that I'm worried about times by the charge on each, all divided by delta T. Now, what I want to do at this stage is simplify it even further. The reason that I want to simplify it further is there's something in here that's very, very difficult to measure. Well, that's not the reason at all. Don't know why I even said that. Now, I'm going to simplify this even further just to bring in another very, very important variable. So what I'm going to introduce us to now is this idea of mean drift velocity. So, write that out. It is the mean drift velocity. And what this is let's imagine you're one of these electrons within this wire, okay? Or in fact, I will draw a new wire so that I'm not getting messed up in all my drawing. I'm this electron. I don't just go straight through the wire like that. That'd be way too easy. Instead, what this electron does, and what every electron does, is they'll bounce around a bit. They might hit the roof and then they'll come back down. Then they'll go into the middle and hit another electron. Then they'll bounce back down. And it's almost, well, it is random. This electron is just moving all over the place. It's drifting. It's not just going from A to B. And because of that, it can be very, very difficult to calculate the average speed of each of them. It's not as simple as just saying they're going in a straight line, speed equals distance over time, because they're drifting around, and if they hit the sides or they hit other electrons, they'll mess themselves up. So we need to define a new quantity, which is the average speed at which they drift, the mean drift velocity, which is little v. Now, from here, okay, I would like to change this equation a little bit. And the way I'm going to change it is I'm going to pull out this big V over delta T. Volume over change in time. And the reason I'm going to do this is I'm going to recognize that the amount of volume that I'm passing per unit time is the same as the cross-sectional area times by the mean drift velocity. And the reason that this is true, and you can kind of do this on your own if you want, is if I manipulate this idea of the relationship between the volume and the cross-sectional area and time and velocity, I'll find that they're actually directly proportional off by a length. Volume and cross-sectional area differ by simply the length of a wire, right? The volume is the cross-sectional area times the length. The time and the mean drift velocity, well, if we boil it down to speed equals distance over time, that distance is going to be the total horizontal distance travelled, and hence they're off also by the length of the wire. So because they both differ by this same constant of proportionality, I can equate them. Now, let's not get our V's confused. Big V is volume, little v is mean drift velocity. And I can replace that V over delta T with simply AV. So NQAV. And this here, I'll write it big down here, I equals NQAV is our last kind of main equation for current. If they're electrons, then this will be an E instead of a Q.